review for chapter 2 or module 2 about polynomials. So as we look at each of these functions, we want to describe its end behavior, right? So as we go farther and farther to the right, what's the graphs doing? So one way to think about it, as we get bigger and bigger numbers like these really don't matter, right? So really we're just looking to plug in really big numbers cubed. So positive times itself 3 times is a positive, right? So that's going to go up, right? Or we can just look at the degree, say, okay, the degree is even, so that should go up and up. But because our lead coefficient is negative, that means it's going to flip down and down. Well, all this one cares about as we go to the right, right? So as we move to the right, this one's going to go down, right? So that's towards negative infinity. Then this one, odd powers normally go like, odd powers normally go down and then up. But because that negative, right, it's going to flip these, so it's going to go up, then down, and again, all we care about is going to the right, so this one is going to go down. So there is our answers for number 1 there. So then looking at number 2, we have this polynomial describing the ideal cut for a round diamond, and then we want to find the domain, the range of this function in the context of the situation, right? So we need to figure out what does f of d mean and what does d mean. Well, d is the diameter of the diamond, okay, and the weight is f of d means the weight of the ideal cut, and d equals the diameter of the diamond. Okay, so that's going to help us in the context of it. Okay, so clearly if we're talking about diameter, we can't be smaller than 0 for our domain, right? So our domain has to be greater than 0, or equal to 0 means we have no diamond. And then weight, we definitely want above 0, right? Okay, so negatives kind of have no impact on this. Okay, so this is a degree 3, and it's a positive lead coefficient, so that means we should go down and up, right? But because we don't care about this one, right, as we go negative, we're not going to have negative diameter, right? Okay, so it normally would be from negative infinity to infinity, right? But because we don't want any nothing, we don't want a diameter size of 0 or negative, we can't have that distance, so it's either one of these two, right? So we're down to one of those two. Okay, and then our range can be all real numbers, but if I get rid of this one, that means I can't go below 0, right? So I can't have my range of all real numbers. So that means I can only go up. So it's going to be this one. Okay, so normally it would be both the domain and range would be all real numbers, but because of the context, it limits our domain and it limits our range as well. Okay, so let's look at number 3. We want to name the degree. So we're looking at the large, because we have a single variable, we want to look at just the largest exponent, and so that is 3, so degree 3. And then lead coefficient, well, what's the number in front of that variable with degree 3? Well, that would be negative 9. And then how many real zeros? How many does this cross the x-axis? It only crosses it once, so there's only one real 0. Okay. Okay, looking at number 4 here, we have Lamar started business 5 years ago. The revenue, what's he bringing in? Can be modeled by this equation. We got an x to the 4th, and so we know we normally go up and up, but because this a on the outside, our lead coefficient would be distributed into all these. So that's going to be negative 0.01 x to the 4th. That means it's going to flip, right, and go down and down, right? And so we want to know where is x, the number of years since he started the business. F of x is the revenue and in thousands of dollars, and so our x is years. Which graph? So we could, what we'd have to do in the y equals, we go to y equals and we could plug this in just like this. Just make sure you have this parenthesis here and this parenthesis here. Okay, and then we kind of compare. You notice that these x's go from, looks like from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so you could make your window be 0 to 8 on your x. Okay, let's make sure these x's, yep, 0 to 8, 0, 0 to 8, and the last one is 0 to 8. And then notice our y's are from 0 to 14. Let's look at these y's. looks like it's 0 to like 5. So this one's 0 to 14, and this one's also 0 to 14. Okay, so if we look at all those, we can see that if we put that in our graphing calculator, I'm determined that it's either this one right here or it's this one right here. Okay, and so if I look closer in, this one is approaching 10 right here on my graphing calculator. This one's approaching 10, but this one down here, the third one, is approaching what, close to 14. And so if I look at my graphing calculator, this is the one that's actually getting close to it on that. So I put my window as 0 to 8 and 0 to 14. Plug that equation in there, see which one it looks at. So this one and the next one kind of seem about the same, but on a graphing calculator, it doesn't go up to 10, it goes almost up to 14. Okay. All right, and so let's look at the next one. We're looking at another polynomial right here. Again, we can type that into the equation and see where it crosses, right? We could look at a table, see where it changed from positive to negative or from negative to positive, and then we can look in between here. Or I can say second trace and go ahead and calculate my zeros, right, to see where it crosses. I do a left bound or I do a right bound, and then I go ahead and guess, and then it'll tell me exactly what it is. Or I can use the table and see which numbers it crosses in between. So I can look at each of these and say, oh, okay, there's one of them, because I know x to the fourth weak coefficient goes like this and like this, and it might cross up to 4 times, right? So I look at that equation in my graph, and I see that it crosses between -1 and 0, and then I also see that it crosses between 1 and 2. So all that's putting this equation into your graph. Make sure you put a negative or subtract in for these two. Don't do the negative button, because that is multiplication in your calculator. Okay, so those two. All right, let's look at the next one. Okay, see here we have Natalia claims that f of x has at least one real zero. Use the table to determine if you agree with Natalia. Then name the interval that the zeros are located on. Okay, so here, again, we don't have really an equation, but we know that when we go from negative to positive, like that, boom, right there, that somewhere there's a 0 between these two, right? So we go negative, positive, there must be one there. Positive, 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 positive. So we can say probably there is one between those two. Now, with here, as long as we go from negative to positive, there has to exist one. Now there could be more between here, right? Because we go from 9 to 11, back to 3, back to 9. So maybe between here where we're at 3 and then we come back to 9, maybe it comes in between those and hits 0, right? Maybe. But we know definitely there's at least one, because we went from negative to positive. So there's at least one somewhere between -3 and -2. So we know that for sure. There might be more, maybe right here or even right here, maybe, but we know we at least have one. Okay, so we agree with her. All right, let's look at this next one. Okay, so here we have this function. We have it to the fourth, but it's a negative, so that means we're down and down, right? And we want to use the table to tell where the relative maximum are. So here we put that in our graphing calculator, and it's to the fourth, so it might cross 4 times, right? Might look something like that. And we want to see where these relative maximum are. Okay, and we can tell that from where we go from, we're going up to 9 and then down to 6. So that means we went up to 9 and then down to 6. So we probably have 1 right there. And then at 6, we go from 6 back up to 19. Then we go up to 42. Then we go up to 45. And then we go down to -26, right? So we can see that we probably have one right here. And then we probably have one right here where we turned around. So somewhere between these two, we probably have a relative minimum. And then here we probably have a relative max. Relative max. Now because it's to the fourth, this one up here is probably an absolute max. So that's one way to do it, is kind of just graph it in random. You could also put this in your calculator and see the graph, see how it goes like this, right? And then you can come here and here, and you can hit second trace, and you can go down to relative max and relative minimum, and then do minimum, and then you can do left bound, right bound, and guess, left bound, right bound, and guess, and it'll tell you those. This one is probably an absolute max. So if we put it in here, we'll see that at 1, so 0 to 6, so at 1 right here is our relative minimum. So our relative minimum is at 1, x equals 1. And then when we bounced back, came up probably at 4. So actually it wants right here. So it is actually after that one. So we went to 42 and then 45. So it's asking for that one. So this one actually up here is what it's asking for. That one right up here as we go to the top. Okay. So, oh, it's probably because we start right here. That's why. So that's why it's not saying 9 is 1, because they're starting right there at 0. So that's why they don't count that one as a relative max. Because who knows, the -1 could be keep going up like that. So that's why they count this one as a relative max, because maybe over here in your graph. So if you graphed it, maybe it kept on going up there. So this becomes the relative max. Okay, so either way, you can look at it, see where you start, see where you end, kind of plot those in your head how it goes, or on paper, or you can put it into your calculator and do the relative max and relative min. So probably somewhere it probably keeps going up and then comes back down. But we just care about from 0 to 5. So you can make your table to 0 to 5 if you want to. Or your window, sorry. All right, let's look at the next one. So we have Helen started a business, and we want to look at her profits. We want to select a polynomial that makes the best model for us. So what we want to do here is we want to go into our calculator. We want to go hit stat and then go to edit. And we want to edit our list. We put on our L1. So you might have to go up to L1, go all the way to top and hit clear. And then hit enter to clear that list from L1 to put in all these. And then go to L2, go up to where it highlights L2, hit clear, and hit enter. So then the list is all clear, because if I have extra numbers down here and not L2 values for these, my function's not going to work. But you can type these in and I can check it if you want me to. Okay, so once you're there, once you hit those buttons, then you can go over to stat. So you go over, hit stat again, stat, and you can go over to calculate. And this one you want to go to number 7. So when you go to number 7, quadratic regression, hit enter. Okay, make sure X list is L1, Y list is L2, and then you're going to go down to where it says store regression equation. Okay, and you can do, on that one you hit vars. So you hit vars, you go over 1 to where it says y vars. Then you're going to hit enter for number 1, and then you're going to hit enter number 1 again, and then you can go down to calculate. And what this does is it stores that equation in there. So when you hit calculate, it'll give you y equals, and it'll say what the polynomial is, ax to the 4th, and then it'll do bx to the 3rd, or it might be some more in between there. But it's going to give you all the coefficients. So A is your first coefficient, B is your second coefficient, C is your third, and all the way down to however many it gives you. Okay, most likely it's probably going to be to the fourth. And so in front of all those numbers, you can just put an X in front of all those numbers except for whatever the last one is. It might be E, it might be D, but so you can put no X on the last one, okay? And then just count up. So that would be a 0 exponent, then it would be 1 exponent, 2 exponent, 3 exponent, and then to all the way back to wherever you get to A, okay? Or you can hit your y equals, and that equation will be put into the y equals. So then you can just copy that equation down from the y equals. That might be easier. That's what the store equation does. On vars, move over to y vars, hit number 1 again, and then calculate. And then you can go to y equals and you can steal that equation. So that equation should be this one with 1, 2, 3, 4 zeros and a 1. So right here, this one. Okay, and you can look at it by looking at your A, and that's going to tell you that very first one. So this problem, all you do is look at what your A equals, and that'll tell you. Okay, so then we look at this polynomial, select all the polynomials. As long as we have a degree, a whole number, that's a polynomial. I'm pretty sure this is probably just after a single variable. Yeah, we're just after, well, no, we can have multiple variables. This one would be a fractional exponent, 1/2, so that is not 1. Okay, whole number, this would be x to the 0, so that's 1. Okay, this has a negative exponent, so that's not 1. And then this one has 2 variables. That's okay to have 2 variables. Okay, and then we just got to look at those exponents to see if they're all whole numbers, which they are. Okay, so it's okay to have 2 variables in there. What is the difference? So make sure you distribute this negative. That becomes positive 9x cubed. That becomes positive 4x squared. This becomes negative 12x. This comes a negative 4. And now we can just combine like terms, right? Like make sure you get all your x to the fourths together. So that would be 4x to the fourth. And then make sure you get all your x cubes together. So x cubed and x cubed, because that became a positive 9, so that's positive 6x cubed. Then get all your x squareds together, so that becomes 9x squared. All your x's, x, and now a negative 12x, so that's a negative 4x, and then negative 11 and negative 4 is negative 15. Okay, next one we're multiplying, right? Because there's no symbol in between there, so that means we're multiplying. So you could do a box method, or you can FOIL it, right? You got to take that one times all 3, and then this one times all 3, right? Or you could do a 2 by 3. So 2 by 3, right? 2x cubed plus 5, and this would be 3x squared plus 7x, whichever one you feel better does it. Okay, and so we multiply these. 2 times 3 should be 6, so I should have 6 total, but I might be able to combine them, right? 1, 2, 3, 4, 5, 6, so maybe these 2, but we might be able to combine a couple too. So we put this together, and we cannot combine any, and so we see that these are most of the same except for this has a degree of 5 and this has a degree of 6. Well, when we multiply, we add exponents, right? So 3 plus 2 is 5. We don't multiply, so this one tries to trick you and multiplies the exponents. 3 times 2 is 6. So same answer except for this one added exponents, this one multiplied. Well, when multiplied by the same base, we add exponents, so this is our correct answer. Okay, look at the next one. All right, we're designing here, and so we want to design a flag for the new school club. Blue square that has been placed at the center of a rectangle as part of the design, and the rest of the flag will be red and yellow striped. We want to use the dimensions of the square and rectangle above to determine which expression can be used to represent the area of the flag that will not be in blue. So basically this one is all blue because it's the square, right? And then we're putting that one like right into here. And so we want to calculate what is this yellow and red part, not blue. Okay, So the area of this one would be multiplying those two. So two things times two things is four things, right? So when I multiply these, I get a 4x squared plus 10x plus another 10x, and then I get 25, right? So 4x squared plus 20x plus 25, 25, not 2x, 25. Okay, and then this one, this rectangle, the area of that would be what? 12x squared, 12x squared, and then 3 times 3 is 9x, 4 times 7 is 28x, and then 7 times 3 is 21. So if we add these together, we get 37 plus 37x plus 21. Well, that's this whole thing, right? But we want to minus this blue area. Well, that would be the area of this one, right? So switching this around, I want to take the 12x squared plus 37x plus 21, and I want to subtract this, right? So that'd be subtracting each one of these. So that would be an 8x squared plus 17x minus 4. So there it is right there, minus 4. That'd be that one. Okay, because I want to find the area in between. That means I got to take the outside area and minus the inside area. Gets my area in between. Okay, next one here we have volume, right? So if I know this height, right, and here's my total volume, can I find the other two dimensions? So basically what to do is just divide. So this one, you can either do it synthetic division or you can do it long division. But here, because this is not, it is a degree of 1, so we can do synthetic division. Because that is a 9, that means we would have to divide everything by 9, which might be okay. But we still have some fractions there. 1/9, negative 12/9, 83 over 9. 45 over 9 works fine because that's just 5. But so maybe long division might be the route to go. But you could do synthetic division. You just have to divide everything by 9, and then you put negative 4/9 into the box, which doesn't seem like it's going to be fun. Right, so probably long division would be the way to go here. And make sure we have a degree of 3, so that means I should have 4 terms, which I do. Okay, if you're missing one, that means you need to put a 0 in its place. Squared plus 1x, and then minus 12. So probably long division might be the route to go. 9x plus 4. So that would be a 5, right? So 5x squared. 5x squared times 9x is a 45x cubed. But 5x squared times 4 is a 20x squared. Subtract those, right? So that would be 0, which I want, right? And that would be 63x squared plus, bring these down, plus x minus 12. Now I gotta ask myself, what times 9x is a 63x squared, right? So that'd be 7x. So 7x times 9 is a 63x squared. 7 times 4 is 28, times x is a 28x. We've got to subtract those, right? That's 0, that's what we want, and then we get negative 27. You notice all those come nicely because they're all divisible by 9. Right, and then we bring this one down. Then we ask ourselves, okay, what times 9x is a 27x? Well, that'd be a positive 3, and we can see we went squared to the first, and now our constant. So we know the rest is the remainder. So 3 times 9x is our 27x. Oh, we need a negative, so that needs to be negative 3. So that makes a negative 27. And then negative 3 times 4 is a negative 12. Now we got to subtract them, so that becomes positive. Subtract that one, becomes positive. We get 0 and 0, so we have no remainder. So that is our answer, 5x squared plus a 7x. So 5x squared plus a 7x, but minus 3. So careful on those negatives. That would be the area of the base. Okay. All right, number 14. Looking at number 14, this negative exponent basically can be rewritten as x plus 6 on bottom, just like that. Right, so this one we can do synthetic division. Negative 6 goes in the box. Coefficients are 8, 22, negative 163. Is anything missing? We got a degree of 3, so we should have 4. 1, 2, 3, 4. Nope, we're good. And now we can go ahead and run it through. 0 on that second row, first column, add those together. We get 8 times that is negative 48. So that'd be negative 26. Negative 26. And times 6. Great. Let's see. Okay. All right, that would be 150 plus 6, 156. So positive 156. Add that, that would be what? 7, so negative 7. That would be 42, and that 44, right? 44. And so that would be negative 2. So negative 2 remainder. Okay, so then we can write this. We start out with an x cubed, so that means this is an x squared. This is an x, that's our constant. And then this is our remainder over what we divided by, x plus 6. And so that one is, those look very similar. Oh, that's a negative 26 and not a positive. There we go. Okay, this one, synthetic division, explain. Write your coefficient as polynomial, write remainder as a fraction, use synthetic division, right? So what would go in the box would be a 3, because it's the opposite. We got to the 4, so we have 5 things. 1, 2, 3, 4, 5. We do. Okay, and we run that through. 12, negative 64. Make sure you get your negatives if you have them. If you have anything missing, put a 0 in its spot. 0 in that second row, first column. Add that 5, 15. Oh man, 27 times 3 is 81. 3 times, what's 3 times 30? That's 90. 90 minus 9 is 81. Yeah, 81, I was right. Okay, so that's 7, 17. 27, 17. 17 times 3 is 51. 51, that is 44. Negative 44. Times by 3 is a negative 132. So no remainder here, because that's nice and perfect there. So we get to 0. So there we go. We started to the 4th, so that means this to the 3rd. This means plus, it's positive, so put a plus in between. This would be x squared. This would be plus because it's positive, and x, and then negative 44 with the remainder of 0. So then we don't even need to write that. There's our polynomial, because it wants you to write as a polynomial. So I need to put it back in there, the x's and x cubes and all that. Okay, this one again, what you got to be careful here is when I'm doing synthetic division, this one, I have to divide everything by 3, right? So that's 6 over 3. So that's negative 71 over 3. So that's 139 over 3. So that's, what is that number? 130 over 3. Well, that's kind of nice. Over 3. And then what I divide here is that 2 also has to be divided by 3. So I get negative 2/3 is what's going to go in the box, which looks fun. Okay. And then run this through. What I didn't mention before is whatever the remainder is, either 4 or 8, right? One of the two there. But you have to write that remainder over what you originally divided by, 3x plus 2. Okay, so you have to do it what you originally did it. I think before I could say you could do it by x, x plus 2/3. You don't want to write it like that. You have to do the original. Okay, so you have to rewrite it as divided by the original. Okay, so when we run this through, all right, this becomes a 2. This becomes a 2. 71 divided by 3, that doesn't work out, so that seems real great. Okay, so this becomes 2. Multiply that. Ooh, we get negative 4/3. But if we subtract that, that'd be negative 75/3, which works out nice, right? Because that is negative 25. And negative 25 times 2/3 is a positive 50/3. So then if we add that, we get 189/3, which is probably going to be That goes in 63. So that's nice, 63. Then if we multiply that, we get negative 126 thirds. So 126 thirds would be 4 thirds. So we get 4 thirds as our remainder. Let's see. So 4 thirds is correct. So, but we want our remainder be over what we originally divided by. And so I wouldn't put 4 thirds here. That is our remainder. But because I multiplied everything by 3, right? So because I divided everything by 3 right here, then I have to come back and take this remainder and times it by 3. So then these 3 would cancel out. So then I get 4 over what I originally divided by. So this is my correct answer. Okay. I guess maybe what you could do, and I would have to check on this, but if I get 4 thirds, I could put that over when I divided by 3. So this would be x plus 2 thirds. I might be able to get away with that. 4 thirds over x plus 2 thirds, but you might as well just multiply by 3 what you divided by originally to make it look like this. So we get an x squared, we get a negative 25x, we got our constant positive 63, and then our remainder was 4 thirds, but because we divided everything by 3, we're going to times by 3, so that could change that 4 thirds to just 4. So 4 over what we divided by, 3x plus 2. Okay, in a binomial expansion, the sum of the exponents in each term is n plus 1, right? And that is false. And so what's that saying is whatever I take, say, a plus b to the 5th, right? When I go through and I do my binomial expansion, I can do my period, but when I get to my coefficients down here, what do each of these exponents always add up to? So this would be x to the 5th, right? This would be a to the 5th. This would be a to the 4th, b to the 1st, a to the 3rd, b to the 2nd, right? It always adds up to whatever the power is, right? Not n plus 1. So a plus b to the n, each of these terms always adds up to n. Now the number of terms, how many terms there are total, right? In your triangle, how many terms are total are always n plus 1, but the power of each individual term is just your n, your power. So this would be false. Okay, explain Pascal's triangle and the expansion of this, right? You would start with 1 at the top, and you would go down on the sides, expanding 1 each time, all the way down, because that's a power of n. I would go down to the n plus 1 row, and then we would look at the coefficients, and we would write down the coefficients, write down coefficients, and then we would start with x to the 7th power, and we would go in descending order to the right, x to the 6th, x to the 5th, and then we would start on the right, last coefficient, start with a power of 7 to the 7th, and then we go to the left in descending order, 7th to the 6th, 7th to the 5th, and so on. Right, so that's how you could explain it. You start out with 1 on top, and then you expand going down, adding 1 to each one, and then you add the 2 numbers above to the left and to the right to get to your next one. All right, so you can say that way. Then we get our coefficients. Once we have our coefficients, we start with the power of x to the 7th. And you can actually just do this example and say kind of how you got each one of those. Okay, the next one to the 4th. Now this one's a little bit tricky because now we have coefficients, right? So now we have coefficients. So if we did 1, 1, 1, 1, 2, 1, this would be row 0, row 1, row 2. Row 3 would be 1, 3, 3, 1. Then row 4 would be 1, or sorry, this would be row 3. Yeah, that is row 4. 1, 4, 6. I need to expand this page. 4, 6, 4, 1. And then the 5th power, or 5th row, would be 1, 5, 10, 10, 5, 1. So this 5th row is our 4th power, n equals 4, right? So these would be the coefficients, and then we would start with our first term, which is 2h, so 2h to the fourth, right, times by 1. So that'd be 2 to the fourth, which is 16h to the fourth, times 1, which is just 16, right? And we can see all those have, except for this one, so we can get rid of that one. Right, then our next one would be a 5 out in front, right? And that'd be 2h to the third. And then what's our second term is an f, so that'd be f to the first, right? So 2 cubed would be 8. 8 times 5 is 40, so 40h cubed f, and we can see none of those are that, so is that a 5? Let's see. Okay, that's wrong. So quick correction here. We're actually not on this one. Sorry about that. Okay, we're actually on this one because I started at 0 here. That'd be row 1, row 2, row 3, row 4, row 5. That's actually row 5 where n equals 4. So that would be a 4. So 4 times 8 is 32. Now we're on the right track. And then our next lead coefficient is 6. That'd be 2h. That was a 3. So this one would be 2. So that'd be 4 times 6 is 24. Oh man, they're all fitting the pattern, aren't they? So this would be h squared. Then f is also squared. Make sure all those are the same. Okay, now here's where the distinction is, right? So we're at 24, right? So that means we can get rid of this one. So now we're down to 2. So now we have either 8 or 32. Okay, so the next one is a 4. This is just 2h to the first, and then f to the third, right? So that'd be 2 times that. That'd be 8. So 8h f cubed. And then we're done. We know probably the last one is f to the fourth. Okay. So sorry about that. I was counting wrong because 0, 1, 2, 3. This is 4, which is the 5th row. Some of you guys already probably recognize that. Okay, last one. Hannah's bookshelf holds equal number of fiction books and nonfiction books. If Hannah selects 5 random books, what is the probability that 4 of those books will be fiction and 1 will be nonfiction? So she has a chance of either selecting 50-50, right? Equal number of fiction. So F for fiction and N for nonfiction, right? Equal number of chances, and she has 5 books, so it's a binomial expansion to the 5th. Right, so this time let's see if I can get it right. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. I'm going to run out of room again. 1, 4, 6, 4, 1. So this is row 0, row 2, count 0, 1, 2, 3, 4, 5. That'd be row 5, but we need to go down to row 6, right? So let's go 1, 1. That'd be 5, that'd be 10, that'd be 10, that'd be 5, that'd be 5, and a 1. Jeez. A 1 right here. That'd be row 5, and then row 6. I'm running into 6, 15, 20, 15, and a 6, and then a 1. So this is the row that I want. So these are the numbers, and I want equal number, right? So they equal have a number of chances. So if I add all these up, that would be my total denominator, the different possibilities of choosing 5 books. Okay, so 1, 6, 15, 20, 15, 6, and 1 gives me a total of 64. And then I want one where it's 4 books fiction and 1 book that. So that would be, this would be fiction would be all 5. This one would be fiction would be 4, and nonfiction would be 1, and that's what I want. So that's the coefficient that I want, is this one right here with a 6, so that I can divide 6 divided by 64, and okay, and of course that doesn't work out, so I messed up again. I'm not counting rows here, I am counting powers. So this row is what I want. So that changes my denominator. 1 plus 5 plus 10 plus 10 plus 5 plus 1. Jeez, 32. 32, and then I want the second one, right? This one right here, so that'd be 5 out of 32. gets me a total of 15.6. So 15.6%. That's it. Sorry about those two mess ups, but that's the review for chapter 2.